Our next speaker is Michael Long. He is a principal adversary emulation engineer at MITRE. In fact, there was a little MITRE reunion happening in the back of the room here. Previously, he was with the U.S. Army. He was a specialist, or he was a cyber operations specialist working across a variety of extremely technical topics. And today, he's going to talk about a growing trend in malware, and that's the use of the Go programming language, especially for its capability for cross-compilation. So, Michael?
So just recapping, this is offensive GoLang 2.0. During this presentation, we're going to give you copious examples of how adversaries are weaponizing Go in the wild. We'll then go through some different techniques that you can use to start modeling those behaviors in the context of your red teaming penetration testing activities. Now, one thing I want to point out is throughout this slide deck, you're going to see lots of examples of techniques with source code. You don't need to feel compelled to take screenshots with your phone if you don't want to. I am hosting the slides on my GitHub repository. I'll also post a link to that after this presentation in the SANS channel. So again, you can get the slides at that URL at the bottom of the screen there. Okay, so just a quick intro about myself. Again, my name is Michael Long, adversary emulation engineer at MITRE. Now, the reason I state that is because in the course of my day-to-day work, I spend a lot of time leading development for a project called attack evaluations. In a practical sense, what that means is I spend a lot of time writing red team tools to emulate different adversary behaviors. So it's that experience that has really informed a lot of the content throughout this presentation. I'll also mention that I'm a student of SANS. I graduated from the SANS MSISE program back in 2018, currently working on my PhD in cyber operations with Dakota State University, both really great programs. Beyond that, you'll find that I'm a really big believer in giving back. I've contributed code to various projects, including Metasploit, Caldera. I've authored attack techniques. I also maintain the offensive GoLang project, and I'm a regular at conference events. Now, when I find that I get tired of staring at terminals all day long, I do like to get out and volunteer. That particular picture was taken in Baltimore earlier in June. We were basically cleaning up a derelict lot. It was a lot of fun. Completely random fact for you. Apparently, if you've been tracking the cost of lumber, which I don't think anybody here does, but it's been going up really, really high. And as a result, we were having to stake those wooden planks to the ground because people were stealing them due to the cost. So completely random information for you. Okay, so what are we going to talk about throughout this presentation? First, what I want to do is just kind of level set and explain why this talk. Why should we as security practitioners care about the Go programming language, or rather use of Go malware in the wild? I'm going to show you various examples of different threat actors, everything from opportunistic crimeware groups all the way to nation state espionage, and explore how are they using Go in the context of their campaigns. With that foundation in place, we're going to shift gears and start talking about techniques. We're going to start really, really easy, and I'm just going to show you how do you start by building payloads, whether it's cross-platform, targeting specific CPU architectures. We'll then progressively get into more interesting territory. I'll show you how to interact with the Windows API to start doing interesting things like injecting shellcode or injecting entire Go binaries into memory without touching disk. Finally, towards the end, I'm going to show you some really neat tricks about how you could use Go from different languages. Now, it's not lost on me. Many people get attached to their different languages. If you do a lot of Windows Enterprise, you might be really big on C#. I'm sure a lot of us are really big fans of Python. These are fantastic languages. Now, what I'm going to show you towards the end is how you can tap into Go functions without even having to learn the language. In other words, calling Go from different languages like C or Python. That's basically the way ahead. So let's start now by just quickly level setting. If you've never heard of Go, this slide is basically for you. So bottom line up front, Go is a general purpose programming language. You can use it for just about any computing task, but it does have those things that it's inherently well suited to address. For example, you'll see Go used a lot for daemon applications, low interaction terminal applications, also in servers. Off the top of my head, there's some prominent red team tools that are written in Go. One you might have heard of is called Go Buster, basically a variant of dir buster. It's really fast, makes use of Go routines, pretty cool tool. There's also the Merlin C2 framework. I believe it's made by the same crew of people that built PowerShell Empire. So similar style framework, but written in Go. So where did Go come from? It was first created at Google in 2007 by individuals including Robert Griesemer, Rob Pike, and Ken Thompson. And if you're unfamiliar with these individuals, they have made immense contributions to the field of computing. They've been around, many of them have been around since the early days of the Unix software. Some of them have created the B programming language, a predecessor to C. More recently, some of them were responsible for the JavaScript V8 engine. So these are basically computing juggernauts who set out to create a language. And what they did is they took some of the best traits that we've kind of learned after decades of lessons learned and experience from other languages. So as some examples, if you run a Go program, you'll find it's really, really fast, kind of like C. It is a compiled language. It compiles to native machine code. So when you run a Go program, it's fast. You'll also find that Go programs, the source code is highly readable. In general, I find I can get up to speed faster with a large Go code base compared to an equivalent in Python. That's just my experience, but in general, you'll find that Go code is highly readable. You'll also find that one of Go's greatest strong points is portability. In Go, it's trivial to cross-compile code for different operating systems and different CPU architectures. In that way, it's kind of like Java in the sense that you write it once and can run it nearly everywhere. The biggest difference is that you don't need to carry around a Java virtual machine or an interpreter like with Python. For the most part, you just compile, upload to target, and it will just work. So that's basically what Go is from a high level. Now let's start shifting gears and talking about why should we care about Go as cybersecurity practitioners? Now, the short answer is simply because adversaries are using it in the wild, and in many cases, they're using it to circumvent modern security controls. On this slide, you can see a couple of data points. These were produced by Unit 42. They have an excellent blog article called "A Gopher" or "The Gopher in the Room," and it's a really great article. Just kind of quickly get up to speed with what is kind of the state of Go malware in the wild. Now, some key points you could take away from this. If you start looking at around 2017, that's really the start of when Go malware in the wild was starting to trend upward. And I think that's a trend that we're likely going to see going forward. You'll also see with that pie chart that as of the time of that article, most of the Go malware was targeting Windows overwhelmingly, and that's pretty much the case with malware in general. But we also need to be cognizant of the fact that it is actively targeting Linux and Mac OS devices. So as we go forward, we have to be cognizant of that ever-growing attack surface. Bear with me. Talking fast, gotta hydrate. So this slide shows you examples of Go malware in the wild. All of these examples were derived from the MITRE attack knowledge base. So just by perusing it, you can find some really good examples of different adversaries and threat actors using Go. So I think all of these are worth exploring in detail, but I'm only going to call out a few just for the sake of time. Take a look at Sandworm team. Sandworm is one of those actors that has been responsible for deploying malware, including NotPetya, Olympic Destroyer. There's an entire book written about that group that's actually really good reading. So Sandworm has been reported to be using a variant of malware called executables, specifically targeting Linux, and it was written in Go. They use this to compromise Linux servers running Centrion IT management software. So kind of a good example of a nation state-centric actor. You'll also see some more run-of-the-mill opportunistic actors. For example, there's Kinsing, there's Rock. They were basically deploying cryptocurrency miners on target, again, written in Go. So mining Bitcoin, Monero, and so on. Now, this last example is particularly interesting. So there's a malware specimen called Ekans. And according to Dragos, they reported that this particular malware had functionality to actively terminate processes associated with ICS operations. So that's really scary. We're just on the cusp of seeing Go-based malware achieving real-world effects against cyber-physical systems. So the big takeaway with this slide is that we're seeing Go malware spanning the entire spectrum of threat actors, everything from cryptocurrency miners to nation-state espionage to potential for attacking cyber-physical systems. All right, so here's the deal. Based on this information, we know adversaries are compromising organizations using Go. To that point, I assert that we, as red teamers and penetration testers, need to know how to model these threats. Likewise, if you're a blue teamer or a defender, you need to know how to mitigate these threats. So two different ideas there. For the purposes of this presentation, I'm going to focus overwhelmingly on the red team applications of Go. I'll try to throw out some quick wins where possible for blue teamers, but this is Sam's pen test HackFest, so we're going to talk about red teaming. All right, so we're going to start with the basics. The idea with this section is if you're kind of new to programming or red team development in general, I'm going to show you how you can go through a minimum of effort to get up and running with a Go tech stack fairly quickly. So installing Go is easy. It's fairly trivial. For the most part, if you use any mainstream package manager, you can do something like Choco install GoLang, apt install GoLang. Takes less than a minute, occupies about 130 megabytes on disk. The Go facilitators do provide graphical installers. So if you're one of those people that likes to click next, next, next install, you can go get those. Now, one thing I want to point out with this, installation is pretty mundane, but let's put this in context. Has anybody here done red team development in C or C++? So you likely know that if you want to develop something in C++, if you're targeting Windows, probably the first thing you're going to do is you're going to go download Visual Studio. So you're going to wait 8 to 20 gigabytes later just so you can compile Hello World. There's a lot of friction just to getting into it. With Go, you just install it. It takes less than a minute. It's trivial. So we know that when the friction for installation is lower, we could expect more adversaries to gravitate to that language and start using it more just because it's easier. So after you install Go, logically, one of the first things you want to do is run a Hello World program just to verify that the compiler and everything else is working. So on this example, you can see what Hello World in Go looks like. It's fairly straightforward. If you look at line 1, you declare a package called main. That's basically the entry point to the program. Line 3, you import the thumped package, basically short for formatted input and output. Then between lines 5 through 7, you actually get into the substance of the code. So when you want to call Hello World, it's very simple. Thumped.println followed by whatever it is you want to send to the console. The reason I really like this convention is if you're dealing with large code bases, it's really easy to trace where different functions come from. Like if I see println and I want to know how it works, I know that it comes from the thumped package. I can go to that package on my file system and actually see how that function actually works. Compiling and running Go programs is also trivial. If you wanted to build this example, Go build followed by the name of the program, and you just run it like a native binary, really, really easy. So next I want to talk about Go's robust development tools. Now this is something that I think we take for granted today, but historically, if you wanted all these capabilities, you had to go on an Easter egg hunt, downloading different tools like DoxyGen, CMake, and so on. As it relates to Go, on a default installation, you get everything from package management to built-in documentation to automatic code formatting. So all that's fairly simple. And let me zoom into code formatting, for example. So if you write a Go program, if you want to format it so that it's uniform and kind of the way everybody else is using it, you use a utility called GoFumped. It will automatically format your program. Now, this is really mundane, but let's talk about why this is important for us as red team developers. Has anybody ever gotten into a debate such as, do we use tabs or do we use spaces? We have brackets on this line or are they on this line? We have some of these pointless arguments that really detract from the problem that we're ultimately trying to solve. The Go developers have rendered that a non-issue by basically saying, when you format your code, you use GoFumped. And for the record, they decided that we're going to use spaces. All right, so now we're going to start talking about building Go executables like a pro. The point here is we're going to show you how you could take some red team-centric programs and build it for a variety of different operating systems and CPU architectures. So one of Go's greatest strong points is that of cross-compilation. In short, you could be developing on a Linux box and simultaneously target both Linux, Windows, or Mac OS. You don't even have to leave your Linux operating system. The inverse of that is also true. You could be on Windows and target Linux, target Mac OS. Likewise for Mac, you can target any of these other different platforms. So cross-compilation from Go is trivial. I'll show you some commands to do that in just a moment. There is also a package for mobile that can allow you to target Android and iOS. I really haven't explored that in great detail, but that is an area if you're looking to kind of see fertile ground for follow-on research. Now, beyond targeting these different operating systems, Go supports over 20 common CPU architectures. And on the bottom of the slide, I've probably listed most of the architectures you're likely to encounter in the wild. Everything from Intel 386, AMD 64, ARM. Something to think about with respect to these different CPU architectures is that our modern enterprise networks are getting increasingly CPU diverse. What I mean by that is you're still going to run into your traditional Windows boxes that are Intel and 386 or 64 based. But you're also going to see a lot of Mac OS workstations. And if you've been following Apple at all, they've moved all their CPUs to the ARM architecture. So increasingly, we're at a point where our binaries may no longer be compatible for different CPU architectures, or alternatively, we just need greater flexibility to write our code once and target all these different CPU architectures. I'll also point out for MIPS and PowerPC, probably less mainstream for what like an end user would be using. You do see it a lot for IoT devices, which are commonly all over the network and usually have far less security readiness than some of your other enterprise devices. So let's talk about Go binaries. The way the Go compiler works is it builds a single native executable. So if you're targeting Windows, the resulting file will be a .exe. Targeting Linux, it'll be an ELF. If you're targeting Mac, it'll be a Darwin Mako executable. You can also build dynamic libraries, so DLLs or shared objects for Linux. I'll show you some commands to do that in a little bit later. Now, some other key points to take away with Go binaries. One is that Go binaries generally have no installation dependencies, and this is a huge selling point for both adversaries and red teamers. The way this works is the compiler statically links the Go runtime and any needed packages. So for example, have you ever written a Python program? You move it to a different workstation, you run it, and it kind of blows up all over your screen. Oftentimes that's because you're missing some third-party package. This happens to me all the time with the HTTP requests library. If you're in Go, that's a complete non-issue. The compiler will statically link all of your packages into a single binary. So for the most part, you upload it to target, you execute it. You don't need any Visual C runtimes on target. You can just run it. It's great. Now, there is a downside with this convenience. When you're statically linking, it inflates the size of your binary. So to give you some examples to put that in context, if you were to write hello world in Go and compile it, it'll likely be around 2 megabytes in size. Compare that to the equivalent C program of about 54 kilobytes in size. Now, for feature complete rats and red teaming tools, they are seldom greater than 20 megabytes in my experience. Your mileage will vary depending on what functionality you put in there. But for implants that I use operationally, usually it's kind of in the 10 megabyte range. A little bit later, I will show you some ways that you can kind of drive that size down without using a packer, which might be frail in terms of AV. Now, I'll point out that some red teamers you talk to will tell them that's a deal breaker. They can't drop giant binaries on target. But I have a different perspective on that. So my thought process is with really, really large binaries, they're harder to reverse engineer because your analyst has to sift through a lot of benign library code to figure out, what is the adversary actually doing. Another thing I'll kind of share with you is I have in the wild encountered AV products that were unfortunately configured to just ignore binaries that were greater than 20 megabytes in size. So it is absolutely a tactic to pad your binaries with benign data for the purposes of AV evasion. So it happens. Personally, I don't think the large Go binaries is really a deal breaker. Excuse me. So what I'd like to do now is kind of walk you through the build process of a red team centric tool. So on this slide, I have an example of a simple reverse shell. Basically, all it does is it runs in an infinite loop. Every 3 seconds, it tries to send a reverse shell to a socket. You can use this with Netcat. You can use this with certain Metasploit handlers, really easy to use. Some interesting things to call out here. If you could see around lines 26 through 32, we put in some logic so that at runtime, the binary will automatically determine whether it's running Windows or it's running on Linux or something else. And in that case, it will call the appropriate shell. So if it's Windows, it'll call PowerShell. If it's Linux, it'll call the Bourne shell. Anybody know why I opted to use the Bourne shell, out of curiosity? The Bourne shell, also known as like /bin/sh, it doesn't automatically log to a history file. So you get a mild stealth benefit there. So we've written this reverse shell program. Next thing we want to do is we want to compile it. So compilation is trivial. If you just want to build for your current operating system, you do go build followed by the name of the program. Another interesting thing you can do is you can run it like a script. Go run followed by the name of the program. It'll run like a script similar to Python, really useful for iterative testing. I also show you examples of how you could target Windows from Linux and the other way around, targeting Linux from Windows. It's just a few commands, very, very simple. On this slide, I show more examples, how to target Mac OS with Darwin Mako binaries. And I've also got several commands showing how you can target different CPU architectures, everything from 386, Intel 64, and ARM 64, just as some examples. Finally, at the bottom, I show a couple of examples how you could do conditional compilation. You probably won't do this for small projects, but if you have a large code base, using some of these build tags or crafted file names will be really helpful in compiling cross-platform code. Now, on this slide, I provide some examples for building dynamic libraries. Now, anytime I'm using these tools operationally, I generally don't like to drop executables on target because we know defenders are hyper-focused on executables. .exe is evil, they know this. In my experience, I found that there's a little bit less scrutiny for DLLs. And it's really to our own detriment. As bad as EXEs are, DLLs are significantly worse. Why? Because they're designed to be relocatable. You can arbitrarily inject DLLs into any remote process to mask your activity in something benign like calc.exe as an example. So with Go, it's fairly easy to build DLLs. Basically what you do is you import the C package. That gives you some native functionality to start dealing with C types. It's a little bit lower level, but not overtly difficult. Next, you have to export a function. If you look at that figure 2 in my diagram there, basically, we're using a comment. That's actually line 10. We're using a comment to export a function. When we do this, we'll be able to call it from any process as a DLL. So here are the commands for building dynamic libraries. Now, I mentioned that it's really easy to build EXEs cross-platform, but in my experience, it's easier to build DLLs from the appropriate operating system. In other words, if you're trying to build a Windows DLL, it's easiest just to build on Windows. I do provide an example showing that you can do it from Linux if you want to, but as you can see, the command is particularly long. It's a little bit unwieldy. But besides that, when you want to build a DLL, you basically just give it the build option of C shared. The resulting file will be something like rshell.dll. If you want to test it, the easiest way to test it is to use something like run DLL32, pointing at your DLL file, and then tell it which function you want to invoke while you're testing. You can also do that operationally. I've done that as well. All right, so up to this point, we've kind of walked you through what the development process looks like just for writing and building a cross-platform Go program. Now I want to start leveling up and show how you can start to do some of those more enticing red team activities. For example, calling the Windows API, injecting shellcode, and so on. So if you do red team development for long enough, eventually you're going to need to tap into operating system functions. You usually need to do this if you're trying to do fancy things, whether it's writing rootkits or injecting code into memory. If you're targeting Windows, typically one of the easier ways to do this is to target the Windows API. Now, if you're coming from C or C++, it's pretty trivial to work with the Windows API. The downside is you have to be a C programmer to be effective in doing that. There's a lot of pointers and data types. It can be hard for your average user. So what we could do is we could use Go to tap into the Windows API, and that basically saves you from having to deal with some of the baggage with legacy C code. Now, there's about 3 ways, at least that I know of, that you can interact with the Windows API. One is to use Go's native syscall package. I'll show you an example of that in a moment. You can also use a third-party library. If you're a beginner, it's far easier to use one of these third-party libraries like W32. They abstract away all the complexity. You just import the library and call the functions that you need. The downside when you do that is you are contributing to that binary size and you're bringing along a lot of functionality you may not necessarily need. A final option is to write the code in C and then basically compile and link it into your project. That's probably something of interest if you're already a really good C programmer. Otherwise, may not be worth your effort. So this is an example of calling the Windows API. On this example, we're basically showing how you could start with a C++ open process. That's basically what you see when you go to the Microsoft developer documentation. And then on this source code, we show examples of how do you import the library, how do you resolve that function address at runtime, and then how do you invoke it. So you can clearly see that this involves a little bit more effort than maybe just using a third-party library. But if you want to start getting really good at Go development, this is eventually something that you're going to have to kind of learn to get good at. Now, on this slide, I provide an example of executing shellcode. So basically what this is doing is it's leveraging WinAPI calls, including open process, virtual allocx, write process memory, create remote thread. This is a very vanilla way of injecting shellcode into memory. Notice that I have a URL pointing to this code. That is just one example. At that URL, I have 3 additional examples, all showing how you can inject shellcode into memory using Go. Now, there's a gotcha when it comes to Go programming that we really have to be cognizant of. And this is also room for a quick win for our defenders who might be watching. So by default, when you compile a Go payload, it automatically includes debug symbols. What this means is if a defender was examining your payload in a debugger, they can trivially derive your source code. So in other words, you build your binary, it kind of ships with its source code, or at least a derivative of it. So this is obviously really, really bad for red team operations. But to that point, I'll say, if you're a defender, make this one of your first go-tos. If you get a Go binary, check and see if they have debug information. And if so, you can derive the source code. Game over. It's trivial to mitigate the malware at that point. So obviously, as red teamers, we don't want this. We want to have some level of OPSEC when it comes to our payloads. How do we take care of this problem? Very easily, we can give the Go compiler some flags to basically say, I want you to strip debug information. I want you to strip the symbol table. The resulting binary will no longer be able to derive source code. And additionally, all of your function names will go from human readable names to hexadecimal addresses. So it's a lot harder to basically analyze that from like a reverse engineering or malware analysis standpoint. There is a bonus to this as well, and it's that it reduces the size of your binary. In my experience doing this, I typically get about a 25% size reduction of my final payload. So you want to do this for OPSEC, also want to do this to reduce the size of your binary. So next I want to talk about additional OPSEC, including hiding console windows. So in general, if an end user were to run a Go program, they'd very likely see a terminal flash up on the screen. We know that that's not great from an OPSEC perspective. So there's a lot of different ways that you could suppress that behavior. If you're dealing with the Windows API and the Go syscall package, you can see highlighted in red there, there are some ways that you can specify, I want all of my processes to have a hidden window attribute. So it makes it really easy to make like a hidden executable on target. You can also pass some Go flags to the compiler, basically that -H Windows GUI, and that'll also suppress the Windows terminal. A cool side effect of this is if you spawn any additional sub-processes, those will also be invisible. So I have used this in the wild before to basically spawn Notepad so that I could inject it, and the end user is basically none the wiser. They don't see Notepad quickly flash and go away on the screen. All right, so up to this point, we've talked about building Go payloads. We've talked about using the Windows API and taking some hardening steps to improve our operational security. Now what I want to do is start getting into kind of some of the next level stuff, some of those really advanced behaviors that we as red teamers and adversaries will be interested in. So memory resident attacks. If you look at any CTI from mainstream sophisticated threat actors, we know that oftentimes they like their payloads to exist in memory without touching disk. And the reason for this is pretty simple. It reduces your footprint on the endpoint. It's typically more stealthy. And it also makes it harder for defenders to recover and study your payload. So typically what you do, whether it's an adversary in a campaign or in a red team operation, you might drop some throwaway dropper or loader on target. You don't really care if that gets burned. What you really care about is getting your important payloads into memory, so it's that much harder to capture and signature. You get a little bit more mileage out of your capabilities. So what I'm going to show you in a moment is how we could use our ability to compile Windows DLLs and then convert them into a format that is suitable for injection similar to shellcode. So here's kind of the process for making this work. So the first thing you're going to do, you're going to write your Go program. It could be backdoor.go as an example. You're going to write your program. You're then going to compile it as a Windows DLL. You can see the command for doing that there. After you compile your Windows DLL, you're going to use another project. There's a really great project called srdi. I put the URL to it in the bottom of my slide. What srdi can do is it could ingest your DLL and then convert it as basically position independent shellcode. So you're going from a high level DLL to shellcode. Once you've got shellcode, you can basically load it using any loader, whether it's something that you have an existing C2 framework, whether it's Metasploit, Cobalt Strike. You could also run your own loader. If you go back to one of those slides where I kind of showed how to inject shellcode, you could use any one of those examples to load the DLL in this manner. So the end result of going through this workflow is you're writing high level code in Go, converting it to a DLL, converting it to shellcode, and then you're free to inject it into memory. That is how you go from high level Go code to in-memory payloads, and it's a really powerful capability. So this last section I have for you entails calling Go code from C. Now, why would we want to do that? The reason for this is because any current programming language that we care about has some kind of foreign function interface to C code. So if we can make our Go code compatible with C, it means we can call that same code from different languages using that programming language's foreign function interface. So let me kind of walk through what this process looks like. So basically, you start by writing the Go code that you want to make compatible with C. The next thing you do is you write some additional code to wrap your Go functionality in a C-compatible wrapper. This is non-trivial. You won't really be able to figure it out just by looking at this slide here. You typically have to get into the developer documentation to learn all the types and all the nuances of converting your Go code into something that's C compatible. But if you're an advanced Go developer, this is very achievable. So you're going to write basically a C binding for your Go code. You're then going to compile it into a static library. Once you've compiled it into a static library, it's really easy to link into any C project. So this basically is a simple C demo program that shows how you can link your Go code as part of that C program. And I'll reiterate too, for all these examples, you can go to those URLs to actually see the source code in its full context. Now, here's how we can really take advantage of this approach. So when we're able to compile our Go code into C-compatible static libraries, we can now import those libraries into other programming languages. This is an example of how we are invoking Go code from Python. And so the takeaway there is you don't necessarily need to know the Go language to benefit from the body of Go source code that is out there. Basically, the way this works is from Python, we're using their built-in C-types library. Has anybody used C-types before? C-types is awesome. You can have a lot of fun with C-types. So using C-types, we're importing our Go library. We're resolving any functions and addresses that we want to call at runtime. We're then invoking that function. And as you can see on kind of that bottom screenshot there, I'm showing what the output looks like if you're running it in a terminal. So again, the whole reason you want to do this is you can write Go code, turn it into a C-compatible library. Now it's trivial to import it in whatever language you want. You can do it in Python. You could do it in C#. In theory, you could do it in Java, but I don't know why you would want to do that to yourself. All right, so that brings us to the summary of this presentation. So we talked at length about why adversaries are using Go. And I think the key takeaways there is it's really easy to use, really easy to get started quickly. It's trivial to cross-compile for different operating systems and CPU architectures. We also saw that with a little bit of experience and knowledge with Go, you can start doing some really advanced things, everything from injecting payloads into memory to invoking Go code from other programming languages. So this is a threat that we need to be cognizant of. And my charge to us as defenders is that as red teamers, we need to continue to model and emulate those threats. So in that way, we can continue to improve cybersecurity. So that's this presentation. Thank you for your attention. I hope you enjoyed this.